Hello, and now we're on to chapter 9, solutions. And we've already done quite a lot with solutions already. So what we should do is look and see what it is we've already learned, what we already know, such as molarity, moles per liter, and some of the new stuff we're going to be looking at. So let's talk about what solutions are, how they're made, and what goes into making up a solution and the different kind of solutions that we see around us. So we want to learn, why do solutions form in the first place? We definitely know already about using molarity to determine these sort of quantities, because when we're looking at concentrations, we're looking at moles and liters. And so we already know that when we're trying to determine reactions, we want to look at moles of different reactants and moles of products. And when we have concentrations, we already have moles right there. So we don't really have to go and figure out how many moles there are in a solution based on the molecular mass and, calculating the molar mass of things. Because the moles are already given for us, and that does make our life a little bit easier. So we're going to be learning about how to calculate molarity when you dilute a solution, because we're going to be doing a lot of that. If you work in a lab, a lot of solutions that you're going to be using are so-called stock solutions with really high concentrations of stuff that you're going to use, because it's easier just to dilute something than it is to make a brand new solution. So we'll learn a really quick method to determine that. And then we're going to sort of look at how solutions are really made right at the molecular level. I've talked a little bit about how important water is in interacting with molecules in solution, but we're going to look at it a little more closely, okay? So solution is just another name for homogeneous mixture. Homo meaning same, and so basically all that means is I can go to any part of a solution and take a little sample, and it will look exactly the same as it does anywhere else. So like something like chicken soup is not a homogeneous mixture, because I can take a little piece one way and I can get a little bit of liquid. Here I got a carrot, there I got a piece of chicken. It's not homogeneous. But if you're looking at tomato soup that you've done a really good job mixing up, it's going to be the same all the way through. So we would call that a solution. Now, there's two parts of a solution. There's the solvent and there's solutes. Now, solvent is just what's the majority of the solution. And generally, that's going to be water for most of the solutions that we're dealing with. But there's also a lot of other types of solutions too that we're going to learn about, such as gas solutions and even solid solutions. So solute is the lesser component of a solution. So if we make a solution of sugar water, we make, like, say, simple syrup or something like that, the majority of the components in that solution is water, and the minority of it is going to be the sugar. So we'd say that the water is the solvent and the sugar is the solute. And that's also true if we make a solution with two liquids in it. Let's say we make say we're looking at wine, for instance. Wine, the major component of wine, is still water. And a minor component of it would be ethanol. Ethanol is also a liquid, but we would also call it solute. Even though it isn't a solid, we would call it a solute because it is the minor component of the solution. Now, an alloy, you've probably heard of an alloy before, that's also a solution, but it's a solution of two solids. So for instance, bronze is an alloy, but it's also a solution because it has two different metals in it. It has both copper and tin, the tin being the minor component. So we would say that the tin is dissolved in the copper, which is a weird thing to think about, that they're both solids, but that's what an alloy is. So I'll ask you a question here and you can think about it. The air we're breathing right now, Is that also a solution? So solvents that are really polar will dissolve solutes that are also really polar or even ionic. And that boils down to the sort of thing we should remember. Like solvents dissolve like solvents, or solvents dissolve like solutes. So if you have two very polar substances, let's say water and salt, NaCl. Salt is super polar. It's so polar it's ionic. And so salt will dissolve in water. But if we have a nonpolar solvent, nonpolar solvents will not dissolve polar solutes. So for instance, if you have something like hexane, which is just a hydrocarbon with 6 carbons in it, that doesn't have any polar groups on it. It's completely nonpolar. And so if we were to take something like sugar and try and dissolve it in hexane, it's just going to settle to the bottom. It's not going to dissolve. Salt poured into hexane is not going to dissolve. It's also going to sink to the bottom. So what sort of solutes would dissolve in a nonpolar solvent? Other nonpolar solutes. So if I was to take, like say, candle wax, we talked about candle wax, or paraffin being a very large hydrophobic molecule. If I was to put that in hexane, it would dissolve. So eventually, I mean, it would take some time, but eventually it would dissolve in the hexane because there would be a lot of nonpolar interactions. And we know those as London dispersion forces, right? Good old LDF. So if there's a lot of London dispersion forces, that's going to be enough to dissolve the paraffin in the hexane. So water is the sort of typical solvent we think of, and we know that it dissolves ionic compounds like salt, and it dissolves polar solvents like sucrose and ethanol that I mentioned before, but it's not going to dissolve candle wax. It's not going to dissolve other nonpolar solutes like cooking oil. That's why when you make salad dressing, you have you have water and a little bit of acetic acid. You have vinegar basically, and you pour some olive oil in it, and maybe you put some other things to give it some flavoring, and you shake it up. It looks like it's dissolved, but what that actually is it's not a solution. It is what we would call needed a drink there. Anyway, we would call that like a dispersion or an emulsion. So what that means is you'd have thousands of tiny particles of oil in the water, but eventually they're going to come together because they have London dispersive forces interacting, causing the large nonpolar molecules, the oil, to interact with each other. They're going to come together, and as they come together, you can see them bubbling, sort of making these large bubbles that then coalesce into great big bubbles, which eventually you get completely separate layers. But the oil layer, which is less dense than water, will float to the top, and the water will sink to the bottom because it's not a solution. The two things do not dissolve in each other. You can shake it up and make it look like they're dissolved in each other, but leave it alone and you'll see that they are not a solution. So these are different types of solutions, sort of giving it away the answer here about air. Air is indeed a solution. It's a solution of gases dissolved in other gases. And if that's true, what is the solvent in air? I'll leave that for you to think about. What would be the solvent? So we can also dissolve gases in liquids. Anyone who's drunk soda has had a solution of gas, CO2, dissolved in liquid. Anyone who's had a beer or wine has had a liquid solution of one liquid, ethanol, dissolved in another liquid, water. We can dissolve solids in liquids, of course. I mean, most of the earth is covered with that sort of solution. Salt water just has a whole bunch of different salts dissolved in water. You can also have gases dissolved in solids. Palladium and platinum metal both can absorb and dissolve a lot of hydrogen gas on their surface. And so we would call that a solution of a gas dissolved in a metal. We can also dissolve liquids in solids. For instance, mercury used to be used in dental fillings. I don't think it's used that way anymore because mercury is kind of toxic. But you dissolve mercury into silver and you would form an alloy which would be resistant to breaking and resistant to oxidation and other sort of breakdown. And then, as I mentioned before, you can also dissolve solids in solids, like brass. Probably everyone's got, like, maybe something like brass candlesticks or something in the house. That is copper as the solvent and zinc as the solute, and the zinc sort of gives it that sort of the shiny, what we call brassy kind of color. So these are some of the definitions, some of the words we're going to be using when we talk about solutions. Now, anything that will dissolve in a solute, we say that it's soluble. Makes sense. So NaCl is soluble in water. Sugar is soluble in water. Oil is soluble in gasoline. Now, something that's insoluble is something that does not dissolve. As I mentioned before, like sugar does not dissolve in hexane or octane, and neither does salt. And oil does not dissolve in water. We would say that they're insoluble. Now, two liquids that dissolve in each other, we say that they're miscible. So that is a special word we use strictly for liquids. And so here we can see this glass over here. We've got oil on the top and the water on the bottom, because we know that even though we can suspend them temporarily, they will eventually separate. The water has like a food coloring dissolved in it, so that's also another solution. And so we can see the water settling to the bottom and the oil settling to the top, because the water can make, as we know, hydrogen bonds with each other. Hydrogen bonds are much more strong in interaction than London dispersion forces. And so water would prefer to be bonding to other water molecules or other solute molecules that it can make really strong interactions with. Now, the oil can't make these interactions. It can't make hydrogen bonds, and for the most part, it can't make these sort of ion dipole bonds, but it can make London dispersion forces interactions with itself. And so if it can't make any of these other stronger interactions, it will make as many of these weaker interactions as possible and coalesce together. So liquids that don't dissolve in each other, like the oil and water, we would say they're immiscible. So not miscible, miscible. So let's identify the solute and the solvent in these particular compounds. Now, heliox is another name for breathing gas, and it has that you would find in hospital. So that is a solution of 79% helium and 21% oxygen. 21% oxygen is approximately the same percentage of oxygen that sort of naturally occurs in the atmosphere that you're breathing right now. But basically all the other gases are replaced with helium. So which one would be the solute and which one would be the solvent? Well, since helium is there in a much higher amount, we would say that the helium is the solvent and the oxygen is the solute. Okay? So if you've ever given your kids Tylenol, you've probably given it to them in liquid form, right? Then it tastes either like grape or bubble gum or something like that. And so for every 5 grams of water in that solution, you have about 160 milligrams of acetaminophen. So which one is the solute and which one is the solvent? Well, this one's a little easier, right? Because the water is there in a much higher concentration. And we typically think of water being the solvent in almost all cases. And the acetaminophen being there in much smaller concentrations is the solute. Now, if you have a different sort of remedy, you've got some sort of herbal remedy, they're normally dissolved in some concentration of either alcohol or water and alcohol, because herbs will have both polar and nonpolar molecules in it, and you want to get them all into solution. And alcohol is, or ethanol or methanol, has both hydrophilic and hydrophobic, or polar and nonpolar interactions possible. So ethanol is a good thing to dissolve a lot of things in, because it will dissolve not only a lot of polar molecules, but it will dissolve a lot of nonpolar molecules or weaker polarity molecules as well. So in this instance, since the alcohol is there in much higher concentration, we'd say it's the solvent. And whatever molecules are in the herbs, we would say that they're the solute. So here I've got hexane. Hexane is a very nonpolar solvent, and it looks like this. 1, 2, 3, 4, 5, 6, or I should say this is one of the ways hexane could look. And the rest are just hydrogens. So you can see why this is a nonpolar molecule, because basically all the bonds are pretty much nonpolar, and it is fairly symmetric all the way around. So it is just nonpolar as it gets. So which of these would it be able to dissolve? Here I've got octane, which basically looks just like hexane, only has 2 more carbons on it. So that would be very soluble. This would be miscible. Octane, we would say, is miscible in hexane. They dissolve together fairly readily. Now let's look at the second example. Let's look at methanol. Methanol looks like this. So we see this is also an organic molecule because it's got carbon in it, but it has a hydroxyl group, the OH group. And so we know that when we have a carbon that's attached covalently to a hydrogen, that can hydrogen bond. So this is a hydrogen bond donor. And another ethanol using this oxygen can accept that. It can be a hydrogen bond acceptor. So methanol can make hydrogen bonds, and it only has a single carbon here. So it doesn't have a long carbon tail that makes a lot of hydrophobic interactions. So actually methanol is a pretty polar molecule. Even though it's an alcohol, it's still a very polar molecule. So methanol is not miscible in hexane. It does not dissolve in it. It's just too polar. And so since methanol makes hydrogen bonds with itself, it's much stronger than the London dispersion forces we would see with nonpolar hexane. And so it's would rather form those molecules, rather form those bonds. It's much, much more stable. And so the polar molecules are going to stay together and the nonpolar molecules are going to stay together. Now finally, let's look at benzene. Benzene has a ring structure that looks like this, the double bond, the opposite double bonds to each other. And so benzene is really nonpolar, and it will dissolve in hexane. Benzene is liquid at room temperature, so when we pour benzene into hexane, the two of them would form a solution. So we look at concentrations. There's sort of two basic concentrations we think about when we're dealing with solutions. One is just the amount of solute dissolved in a certain amount of solvent, and there's a lot of different ways we talk about concentration. The one we're most familiar with, of course, is moles per liter, or molarity. That's the most helpful to us when we're trying to calculate how many moles are involved in a reaction. But there's a lot of different ways that we're going to talk about that we can mention concentration. Like in the hospital setting, a lot of times we're not particularly interested in how many moles. For instance, looking at the oxygen helium example, it's not really that important to think about the number of moles of oxygen and moles of helium. We just want to know what the percentages are. So that would also be a concentration. The other thing we want to think about with solutions is how soluble some things are. That's like the limit of how much solute you can dissolve in a certain amount of solvent. Because all of us have made, like, a solution of sugar, a solution of salt in water, and you stir it up and you add a little bit more, and you stir it up and you add a little bit more, and you notice that the more and more solute you add, the longer and longer it takes for it to dissolve, until eventually you add more solute and it just doesn't go into solution anymore. And you can add as much more salt or sugar as you want, and it's not going to go into solution. We would say you have reached the limit of the solubility of sugar or salt or whatever it is in that amount of water. You can't add any more. So these are some of the various solutes that are soluble in water and that are not soluble in water. So have a look. Notice that some things like silver chloride are really not very soluble at all. In fact, silver chloride is like the old-timey photography with black and white photography used silver, and with a reaction of silver interacting with chloride. And so silver nitrate is soluble, silver chloride is not. And so you would expose the film that had silver on it, treat it with chloride, and then wherever the silver was, it would form a precipitate, and you get your picture. We can see that benzene, as I mentioned before, is a very nonpolar molecule, not terribly soluble in water. You can get very, very little of it to dissolve. You can get some of it to dissolve, but not very much. Now look at some of these other ones. We've got calcium nitrate, really soluble. You've got glucose, very soluble. Salt, in both potassium bromide and sodium chloride. You see potassium bromide's even a little more soluble. And sucrose, very, very soluble. What's similar about all of those that's different from the things that aren't very soluble? Think about that. So a saturated solution is a solution that can't dissolve any more solute. So it is absolutely filled. So it is at its limit. So if the limit, let's say, of, I think it was salt, was around 40 grams per 100 mils for sodium chloride. Once you've reached that 40 grams in your 100 mils of water, that's it. You can't add any more. And so we would say that's a saturated solution. We can't put any more salt in that water. Now, something below that amount is unsaturated, meaning we can add more salt and it will dissolve in solution. Now, notice here, in a saturated solution, when we start to add more solute, you get something called nucleation. Nucleation just means that a crystal will start to form at that particular spot because you've got a lot of salt molecules running around, and basically all of them are interacting with water. And basically all of the water is taken up interacting with salt molecules. There are no more bonds to form with new solute molecules. So if you put new solute molecules in, basically the only interactions they can form are with each other. And so you have this event where you have two and we'll talk about this in a minute, unsolvated crystals come together and interact with each other with ionic interactions. We know ionic interactions are really, really strong, right? So they interact with each other with ionic interactions and form a solid and fall out of solution. So these are some of the things that affect solubility and what is a saturated solution. So as I mentioned, if you keep putting salt or sugar or whatever it is you've made a saturated solution of in water, it's not going to dissolve. And so here we have a saturated solution and someone's pouring more solute in it, and it's not going to dissolve. It's just going to sink to the bottom. You're not going to see any increase in the concentration of that solid in the water. So what's actually going on here? Well, what we would call that is an equilibrium. We haven't really talked much about equilibrium, but equilibrium is basically a reversible reaction. It can go in one direction, it can also go in the other direction. And when reactions are going in opposite directions, basically when you get to the point where it can't go in one direction any longer, like dissolving salt in water, it will keep going in the dissolution or solvation direction for as long as there is water to interact with salt. Once we've run out of water to interact with the salt, once it's all interacting with salt and there's no more interactions to make, the reaction is going to start going in the opposite direction, where you're going to have things start to undissolve and fall out of solution. And so when you see this large amount of solid in the bottom, you're still dissolving things, but for every salt molecule that goes back into solution, another salt molecule falls out. One salt molecule goes in, one salt molecule comes out. And you're in this sort of state of equilibrium where you can't add any more net salt molecules to it, because for every two you dissolve, two are going to just fall right back out again. So this is going back and forth, and we represent this with an arrow going in both directions. So I've got salt going in solution, and I've got salt coming out of solution, both at the same time. So if they're both those reactions are happening at the same time, I can't add any more salt. Any more salt I add is just going to push this reaction in this direction. So I'm basically stuck with the amount of salt in a saturated solution. This is one of the examples of saturated solutions in our body that's kind of nasty. So we get gout, Gout is sort of back. It used to be like, sort of the rich man's disease. It's sort of back now. And the solid compound that falls out of solution is something called uric acid. And this is what uric acid looks like down here. So we can see that uric acid can make a lot of both hydrophobic and hydrophilic. It's both polar and nonpolar. It's both. We have all these polar interactions around the outside of it. And on the inside of it, we see a lot of carbon-carbon bonds, carbon-nitrogen bonds that are nonpolar. So the interior of it is nonpolar, the exterior of it is polar. But you get enough of them together, and you can see that these rings here, these are the rings around the interior. If you get enough of them in one place, they start to stack on each other, and they fall out of solution, because basically that is a strong interaction, strong London dispersion force of these things stacked on top of one another, and they'll fall out of solution. And the problem is when they do, you get these like thin needle-like crystals that form, generally in the ankles and the feet, and it's really, 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 really painful. So luckily there's treatments these people can get, and special diets that cut down on the amount of uric acid. Now, kidney stones have a different crystal that falls out of solution. It's called calcium oxalate. And this is what calcium oxalate looks like down here. So it's oxalic acid when it's not complexed with calcium. And oxalic acid would have a negative charge here and here on those two oxygens. But we know that calcium ion has what charge? +2. And so the calcium ion, when it comes in contact with oxalic acid, makes this complex right here, where now everything's no longer charged. We basically have shut down those two negative charges and complexed it with calcium. And if you have a look, this kind of looks more symmetric than it did before, because we have an oxygen here, one there, and none of them are charged. And so it looks relatively symmetric. So it becomes sort of more nonpolar than it was before and falls out of solution, and you get these kidney stones. And anyone who's had kidney stones or knows someone who had kidney stones knows it's incredibly painful. And so generally the treatment is you break them up into very small pieces and pass them, which, believe me, isn't a whole lot of fun. Now, when you're dealing with solubility and temperature, you have to look at what is the solute we're dealing with. So the solubility of most solids dissolved in water goes up as you increase the temperature. And that kind of makes sense, because you start having the water molecules moving around more, and it does two things. It sort of leaves more space in between the water molecules for the solids to fit in there, and a lot more of the interactions would be lost from the water molecules interacting with each other and made more available to interactions with the solute molecules. So generally, that's a good thing. And so, like, for instance, going back to the making sugar and salt solutions, when you have cold water, you can dissolve a lot less salt than you can when you have hot water. Same is true with sugar. So you can heat up a sugar solution that basically, where you have some sugar at the bottom, basically you get a saturated solution. If you heat it up a little and start stirring it, that sugar will now go into solution. So you can manipulate the solubility of most substances by increasing the temperature. However, with gases, that is exactly the opposite. And again, that sort of makes sense too, because gas molecules in general like to be moving around really, really quickly, right? So I mean, that's the definition of a gas. And so if you increase the temperature, you start moving not only the water molecules around, you start moving the gas molecules around too. And as the gas molecules start moving faster and faster through the solvent, eventually they'll just start moving so fast that they just pop out of solution. Like if you take some Coke, for instance, and warm it up, you will notice that the CO2 that's dissolved in it will just start bubbling up and leaving the bottle. Because the solubility of the carbon dioxide in the water is a lot less in hot water than it is in cold. So you need to keep carbonated beverages cold for a number of reasons. One, they just taste better. And two, the carbon dioxide remains more soluble in cold liquid than it does in warm. So if we look at the gas dissolved in water and other solutions more closely, it was realized quite a while ago that there's a relationship between how soluble that gas is in solution and whatever the pressure is above it. And we've probably noticed this again with soda. If you have a can and you open it, what happens? You hear that as you open it, right? Immediately CO2 starts popping out. The reason for that is you have, by opening it, have reduced the pressure inside the can. The pressure inside the can before you opened it was much higher than atmospheric pressure. That is because the companies want the gas, the CO2, to stay in solution. So if you put more pressure above the liquid, more of the CO2 will stay in solution. The minute you open the can and you lower the pressure to atmospheric pressure, the gas will then escape. And so pressure will be released and the CO2 bubbles out of solution. And we also see this during breathing when we're exchanging carbon dioxide and oxygen. When we breathe in, we have a higher relative concentration, or what we would say partial pressure, of CO2 in the air than in our blood. And so since the concentration or the partial pressure of oxygen is higher in the air in your lungs than in the blood circulating through your lungs, the oxygen gets dissolved in your blood. It goes into solution because the pressure outside of the blood is higher, so it goes into solution. Now the very opposite happens when you breathe out again, because as you breathe out, the partial pressure of the CO2 in your blood is now higher than the atmospheric pressure. The atmospheric pressure of CO2, even though it's going up constantly, is much, much lower than it is when you're in your blood as you're breathing out, because that's what your lungs do. Basically, they exchange oxygen for CO2. So on the way back out again, the CO2 pressure inside your blood is much, much higher than it is in the atmosphere. And when that happens, the CO2 goes out of the blood and into the atmosphere. And then you just repeat the process again. You breathe in, the O2 concentration is much higher than it is in your blood. The O2 goes in, and on the way out, the CO2 pressure is much higher in the blood than it is in the atmosphere. So gases will go from where the pressure is high to where the pressure is low. So wherever, it'll just move in that direction automatically. So like I mentioned, there's a lot of different ways of looking at concentration. This is one. So we're going to look at percentages. And the first is mass to mass percent. And this just relates the mass of whatever solute we're talking about to the mass of the solution. And that's the key I want to point out here. When we talk about percentages, we're always talking about the mass of solution, not the mass of the solvent. There's a couple of rare instances that we would deal with the mass of the solvent, but most of the time we're dealing with the mass of the solution. So we would have the mass of the solute on top, and on the bottom we would have the solvent plus the solute times 100. So remember that. That's a key to doing these sort of calculations. So the first one is just percent m over m, or mass to mass. We just say a mass to mass percent. We would also look at a volume percent. You would see this typically when you're dissolving one liquid in another liquid. Like a lot of times you will see like alcohol dissolved in water, or if you have a percentage of a lot of different liquids dissolved in water, you give them as a percent volume over volume, like hydrogen peroxide, for instance. Actually, I think that one's a mass over volume. So I may have to check the bottle. But if you have two liquids, basically you look at the volume of solute over the volume of solution. So in that instances, again, you have to take the volume of the solvent and the solute on the bottom. Add them both together. Now for a mass to volume percent, that you see this a lot in hospitals when you need to give a certain mass of a drug. Let's say, because a lot of times drug amounts are given in milligrams or micrograms or whatever it is. So you have a certain mass of that drug dissolved in a certain volume of solution. So like a glucose, I think, is basically like a Ringer's lactate solution, all that kind of stuff, are basically given in the mass of lactic acid, glucose, all the other different things that go in it, in a certain volume of solution, because the patient needs a certain mass of particular substance per kilogram of their body weight, sort of thing. So in that instance, we look at the mass of something divided by the volume, because there we're not particularly interested in calculating moles for doing concentrations. We're interested in maintaining a certain amount of a drug, a certain amount of another molecule in the patient's body. And so we need to know what the mass is rather than the number of moles. And then when we're dealing with really dilute things in water, we would express them in terms of parts per million, ppm, or parts per billion, ppb. They're both mass-based. And so generally these things are so dilute that we don't even need to consider the mass of the solute when we're considering the mass of the solution, because the mass of the solution is basically 99.9999% of the solution. And so adding the mass of the solute really doesn't change it much. And we would use these, generally we use these a lot for things that are particularly toxic, like when we're measuring the amount of lead in drinking water, we measure it in parts per billion because it's so toxic, to children and everybody else, that we want to be able to detect it in very low concentrations. So we would take the mass of the water and we would see how many grams of lead would be in there, and then multiply that by a billion, because that number is going to be really, really, really small. Let's look at an example here. So if I have dextrose, which is just another name for glucose that can be broken down. It's a solution with a mass of 2.00 times 10 to the second, which is just another way of saying 200 decimal grams. If it has 15.8% of dextrose dissolved in it, what's the mass percent of this solution? So the dextrose solution has a total mass of 200 grams. The amount of dextrose in it is 15.8 grams. So in this particular example, we do not have to figure out the mass of the solution because it's given to us. Because the dextrose is already dissolved, it has a mass of 200. So we put the 200 on the bottom because that's the mass of both the solvent and the solute. The solute is 15.8 grams. And remember to multiply the whole thing by 100. So when we do the calculation, we get 0.079. So then we try to figure out what do we report as our percentage, because we're going to multiply this number by 100. So if we multiply this number by 100, we get 7.9%. But we have 3 significant digits in both masses. In both 15.8 and 200.0, we have 3 significant digits. So since this is 0.079 with infinite zeros after it, we would say that our percentage is 7.90%. Okay? So now, in this instance, we have glucose dissolved in water, and we have a 12.75 mass to volume percentage. Now, what does that mean? It means 12.75 grams of glucose for every 100 mils of solution. And so the question is, what volume of that do we need to obtain 50 grams? So 50 grams times, now remember, we want a volume. So we want to arrange our unit conversion so that we get volume at the end. Well, my volume is on the bottom and my grams are on the top, so I'm going to flip that upside down and put 100 mils over 12.75 grams. See, that cancels out my grams, and I am left with 392.157 mils. So now it's just a time of trying to figure out how many significant digits should we use. Well, I've got 4 in the concentration of the solution, but I've only got 3 in the number of grams I want back at the end. So we go 1, 2, 3, and our answer is 392 mils. Okay? Now molarity, I should know molarity by now, right? Just moles of solute over liters of solution. That is the most common method of using concentration when we want to deal with reactions. If we're not particularly interested in reactions, a lot of times we will just use volume over volume, or mass over volume. If all we are interested in is a mass of solute, then we'll just use a percentage. But as chemists are generally interested in a reaction that takes place between 2 solutions. So they need to know how many moles are involved, and that's why we use molarity. more frequently than anything else. So if we're doing a stoichiometry calculation, if we have the mass of one solution and we have a concentration of another one, then we'll have to figure out the moles using the mass for the first substance, but we'll just use molarity for the second one. And we know that that's much, much easier because it already tells us how many moles there are in a liter. So once we figure out how many liters the volume is, moles is really easy to do.